Okay guys, let's start the lecture. Okay, so we're going to continue on the track of state space modeling and state space method. Okay. Yeah. So today we're going to talk about the concept called controllability, observability. And if we got time, then we're going to go on to pole placement controller. Okay, so pole placement control design. Okay, so let's talk about controllability concept first. Okay. Okay, so what we're considering is we're considering a discrete system, and let's write down the discrete system here. So we're mainly considering SISO system, so I'm going to skip the F vector signs that are here for the U vector that are here, right? In the lecture notes, you probably will notice a slight change of symbols. In the first lecture, when I use the discrete one, I use A and B, but from here, in the lecture notes, I use G and H. It's kind of just to be more consistent with the notation in the textbook, right? But really doesn't matter. Okay. So G in general is n by n matrix, okay, and H is n by 1 matrix, of course. Right? Yeah. So controllability basically means here's a vector of state variables. Okay, so there are n number of vectors, n number of components that are here. So those are state variables, right? And the whole purpose is controlling. Controlling means here is your input U at here. Here's a U. So the idea is, are you able to control each one of this at here? Or in other words, do you have this U? Does the U at here have a control over x1 to x2, or does U at here have effect on x1 to xn here? Right. So that's the question here. So basically, does U of k at here have control or any effect on x of k at here? Okay. Yeah. So let's say, suppose having control basically means, look, here's x1 of k, right? And I want x1 of k to go back to 0. Okay. So maybe initially x1 of k is, who knows, maybe 1 or 2 initially, right? So if U of k has effect or has this direct control over x1 of k, then it could be brought back to 0, right? However, maybe not, right? Maybe U of k doesn't have the effect, so it doesn't really matter how big this is. X1 of k is not affected by this U of k. Okay? Then in that particular case, that state is called uncontrollable. Okay? Does that make sense? Right? So controllability basically is all about this concept right here. Right? Yeah. So here's the definition here. So the system, okay, the system said to be completely state controllable. So completely state controllable means every one of the states at here is controllable. Okay, completely state controllable. If there exists a piecewise control signal okay, u of k. Yeah. So why is it piecewise? Because it's discrete, and defined over a finite number of a sampling period. Okay. Yeah. So in other words, yeah. So basically, let's say you're asking is, I want this x of k. Basically, here is what you want is you want x of k. Okay. To be transferred, okay, to, let's say, to be transferred like this from x0, okay, here is your initial condition, to where? To a final state, xf, okay, to a final state. So we don't know what this final state, but it may be defined by the user. Okay. So that's basically what it means here. Giving, right, giving a set of u of k, basically. Right? Yeah. And this x of f, right, will be the final state. Okay. So if this u of k exists, so basically you can find mathematically, you can find a set of value u of k, so that you can bring it from initial to the final state, then it's completely state controllable. All right. So let me write this in a more mathematical way here, and then let's look at it, the definition, okay, in a more mathematical approach. In the previous lecture, okay, if you remember, we have derived the so-called solution of this discrete system, right? Solution. So what's a solution? Basically, here is a difference equation. I'm looking for a solution, basically looking for a general solution, x of k in terms of x of 0. Right? And in front of this one here, there's so-called the state transition matrix. Right? Yeah. So let's write down like this one here. Okay. There's one more word here. We want this one to be transferred from initial to the final state, giving a set of this here in at most, okay, n sample period. Okay, sampling period. So n at here is the order of the system, or the size of the matrix, right? Size of the system matrix. Okay, so now if I write down, let's say, what would be the value of x of n, right? Basically, x of n, what would be the value of xn in terms of your initial state? If you apply the formula for the solution of the system, okay, it would be g to the power of n, that's a state transition matrix, okay, and then plus, okay, gn minus 1 h u of 0, okay, plus gn minus 2 h u of 1 and until and h u of n minus 1. Okay, so this is a solution, and this is what we derived in the previous lecture. It's actually quite easy. You just iteratively, right? Iteratively, you can derive at this expression in here. Okay, yeah. So this is x of n equal to this. So let's take a look at this x of n here. Okay, and let's move this term. Okay, let's move this term over to the right, to the left. Okay, so then what do we have here now? Okay. And then on the other side here, it's this whole chunk right here. Okay, this whole chunk. So if you look at this whole chunk here, if I write it in the matrix format, okay, this whole thing here, if you write in matrix format, and I can write it as multiplication of two vectors. One vector here is this u vector. Okay, one is this u vector here. Sorry, the other way around. Okay, one is this u vector. And the other vector here is the coefficient in front of each one of the u components at here. So you see, what's the component in front of u n minus 1 here? It's this h at here, right? And what's the component in front of this u of 0 here? It's what? That's the g n minus 1 h at here. So the second one here should be gh at here, and then dot 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 right in the middle here. Okay, can you see this? Yeah. Okay, so let's examine this one here, and let's see what's the purpose of doing this one here. Now, let's suppose that if this is the final state. So suppose this is your final state here. Is that okay, right? Fine. As I said, final state is what you want, right? What user want. Okay. If this is your final state, so basically means what? This is a known quantity here. Okay, this is known. And this g to the power of n, the g we know that's a system matrix, right? This is know that. X of 0, that's initial condition, so this is also known here. So altogether, these two terms here, they all known here, right? We all know this. Okay, we all know this. And if you look at this matrix right here, okay, so for SISO system, as we write it down, this h, what's the size of h here? N by 1, right? Okay. So this is n by 1, and what's the size of G? Matrix. N by n. N by n. So G multiply h give us a size of what? N by n. N by n. No. N by 1. Yeah, n by 1. Right. So G is n by n. H is n by 1, so this is, so basically this is n by 1, this is n by 1 here, right? So all of this column here is the n by 1 column here, okay? So guess what's the size of this matrix then? N by 1? No. Each column, this matrix has many columns here. How many columns does it have? 1, 2, up to here. How many columns does it have? So look how many G's there. This is no. So this is G of 0 here, right? How many columns? The G's starting from 0 up to n minus 1. So there are n columns. There are n columns. Each column is n by 1. So this is actually a what? N by n matrix here, right? N by n matrix. So this is an n by n matrix, and multiplied by this n by 1 in here. Okay. So what do we want? We're according to our definition, we're saying is if there exists a piecewise control signal u of k, such that this set of a piecewise u of k can bring your state variable x of 0 to x of final state, then the system is said to be completely state controllable, right? Yeah. So the whole idea is basically you have your final state defined, you have your initial values there, and then you are saying is do we really have a set of this U of K at here such that you can bring this initial to the final here? No matter, right? So based on this observation at here, how do we know whether this exists or not? So you can see now, if you look at this one here, this side here is known, right? And this is a matrix, maybe let's use M. This is a big matrix M multiplied by a vector at here, right? Multiply vector. What do we want? We want to know if this one exists or not. So basically, you have to, if this one exists or not, depends on what?
Size of
not the size of the matrix. So, well, if I write it this way here, AX equal to B. So B is known. Under what condition that this X exists?
A is not singular.
Exactly, right? You're solving basically for X. So under what condition? Only when A is invertible, you can solve for the X. So then, coming back here, if I want to have a set of U here such that exists and it satisfies this condition at here, then this matrix at here has to be non-singular or full rank, right? Full rank. Okay. So this is basically an alternative way of describing this completely state controllable. Okay, so let me write it on here again. So this matrix H, GH up to Gn minus 1H, okay, and it's called controllability matrix. Okay, it's controllability matrix. Then the necessary and sufficient condition. Okay. So the necessary and sufficient condition for the completely state controllable is then this matrix needs to be full rank. Okay, so let's see, I'm writing in this one the rank of this matrix is a full rank. Full rank, the matrix size is n by n, so the rank here is n at here. Okay, rank is n. Was that good? Yeah. So that's basically state control over here. It's just like that. Okay? Yeah. If this is a full rank at here, basically you can bring your state value from your initial to the final, okay, in at most how many? N number of steps or n number of sampling period. If the system orders 2, so you can technically you can find a set of U at here, so then you can bring that to the final within 2 steps. Okay, yeah. Okay, so any questions? Are good? So now let's take a look at the second concept, observability. Okay, so observability, so what we do is, let's consider this one. So I'm skipping the U there, so for the time being. So basically, actually, you don't need a U there. Okay, we won't need that U. oh, sorry, I actually didn't you, but let's use this as an example here, right? Example. Okay, so if you look at this simple one here, okay, if you look at this simple one in here, so one of the situation in general, very common situation is this. So let's say maybe what you have here, you have a sensor. Let's say you have a position sensor. Okay, a position sensor. Okay, and you don't have a velocity sensor. You don't have a position sensor here, right? Yeah. But you have probably a system, let's say a DC motor system here. Okay, and then you will be able to derive a set of state space equation. So one of the state, let's say one of the state may be represented the position, and the other state is a position. It's a state variable representing the velocity. Okay, yeah. So in this case here, okay, you have the sensor measuring the position, but you don't have the sensor measuring the velocity here. Okay, yeah. So then, what you really want is when you design your controller, you still need the information of the velocity, right? Yeah. So example, if you design a PID controller, and one of the control part is that KD, the derivative part, right, multiplied by basically the desired velocity minus the actual velocity. Okay, yeah. So you need that velocity information for the controller. Okay, but you don't have the sensor to measure this velocity here, right? Yeah. So then in this particular case, then what do we do then? So as later class we're going to see is we're going to learn a technique so-called use observer. Okay, so we can use an observer, okay, to approximate or to observe velocity from. So we can use this from position. Okay. However, okay, before you can do this, right, there is this assumption, this premises set here, you get to satisfy here, basically, the system has to be observable, basically, okay? So that's the idea here, so observability. Okay, so system has to be observable here, all right? Yeah. So what makes the system to be observable? Now, if I go back to this simple assumed example here, so I have a position. What's the position? Position, let's say, is the output at here. So basically, when you use a C multiplied by X, maybe the C is just a 1, 0. So when you use a 1, 0 multiplied by this state variable, you have this output here, right? And the output is basically just the position at here. Okay? Yeah. So your output, okay, your output is only the position. And you're going to use the output, trying to basically use the information in the output to trying to observe the unknown information, the velocity there, right? Yeah, so that's the situation here. Okay. So in order to observe a certain unknown state there, okay, then there has to be certain relationship needs to be satisfied here, right? Okay, so now let me. Maybe I should write down the complete one here. So let's write down the use the complete one here. Okay, let's use this one here, right? So we'll still start from the solution of this discrete model. Okay, solution of discrete model. So if you remember the solution discrete model, just as what we just write, x of k equal to gk x of 0, okay, then plus, okay, k minus 1 here, g equal to 0 here. Okay, so this is the solution at here, right? This is solution. And the y of k, okay, will be c multiplied by that, and then c multiplied by this chunk at here, and then plus d u of k. Okay, so plus d u of k. So what does this expression, second expression, tell us? Okay, let's imagine the situation, the actual control situation here. Okay, actual control situation. So you have a system. You put in some control input to the system, right? And this u of k representing is the control input. And what did you put? You put u of 0, and you put u of 1, and you put u of k into the system, right? Okay, so basically this is what you put it into the system, so you know what it is, right? So basically this is known here. Okay, this is known. Okay. And if you look at this term here, okay, if you look at this term here, this is everything is about the u, and everything is about the g and h. So basically this term is known, right? If you have this input, you have the control input to the system, then you have this term here. Okay, you have the value of all of this one here. So you do know all of this one here. Okay, so you do know all of this. Okay, and then the only part that you look at this one here. So what else do we know? Y of k is the output, right? Y of k is the output. So this is y1. y0, y1 up to y of k. Okay, so we also know this term in here, right? This is what this one we also know it here. Okay, yeah. And this c at here, this g here is the system matrix, and this one here we also know here. Okay, we also know here. So it's just this x of 0 here we don't know. So this is like a reversed problem here. I wanted to observe the system. Then if I can prove this based on the known here, this is known here, okay, and this is also the coefficients known here, can we backward to derive the value x of 0? You see what I'm saying here, right? See, the previous one is initial condition you assume is known, but in this case here, let's assume initial condition we don't know. So let's say based on the collection of the data, collection of the system information, which is what? Input, output. Okay, here's the input, u. Here's output. Okay, here's output here. Okay, can we basically, this is known here, output. Okay, here's output. So can we derive the information of x of 0 based on the input and output here? So the question mark. Okay, derive this guy here. If this is a yes answer, then the system is said to be observable. Okay. If not, then it's not observable basically. Okay. So if you can get all the states of the x at 0, then it's observable. All right. Yeah. So now let's get back to here. Okay. So let's see how do we make a decision at here. So as we said, this whole chunk at here is known, right? This whole chunk is known here. Okay. If I move this whole chunk to the left, so this is basically a known minus another known one. Okay. Yeah. So when we do this, maybe we can actually just simplify the situation here. If this is known, let's just consider what? Let's just consider this equal to this. So we can simply just consider this y of k, okay, equal to c gk and x of k here. So we can simply just consider this. All right? Yeah. If I just simply consider this now, okay, so then let's set up ourselves a set of equation at here. Okay. So I have y of 0 equal to, when k equal to 0, we will c x of 0. Okay. And we can set up the next one, y of 1 equal to cg x of 0. Okay. Up to what? Up to this y, let's say n minus 1 and here equal to cgn minus 1 x of 0. Okay. Yeah. Let's set up ourselves some equations at here. Okay. So remember the purpose. Okay. The purpose is to obtain, okay, this x of 0 here, okay, based on the known quantity. Okay, known quantity here. It's a simplified situation. The left side here really should have all the information to use, but because there's just a known one here, so let's just simplify the situation right here. Now, if I examine this one here, how many states do we have? The state is an n by 1 in general, right? The x is a n by 1 state vector. If I look at each one of this here, so let's say suppose, okay, this y, this is output y, there are m number of output. Okay, let's say the size of the y is m by 1. All right. If the size of the y is m by 1, then what is the size of the matrix C? So x is n by 1, y is m by 1, so the size of C is actually m by n, right? Okay. So C is n by n. Then if you look at each one of them at here, for this one here, actually how many equations do we have for each one of them? For each one of them, how many equations? No, not to guess up to where. C is m by n. What's the n? Y vector. Y vector is n by 1. There's m output. So basically, if I look at each one of them, it's like this, right? y1 of 0 up to how much? ym of 0 equal to what? Equal to a m by n matrix, then multiplied by an n by 1 vector here, right? So, and this is 0 here, okay? So that's just the initial state 0. Okay? So, that's just for one of them, right? That's just for one of them. How many equations do we have just for one of them? How many equations? We expand it out. How many?
N by n.
No, equations, no. If you expand them out, okay, maybe I'll use a number here. So what's the y of 0, y2 of 0? Let's see, m is 2. Here is 1. This is let's say 2 by 3. Let's see, 1 2 3 3 1 4, and multiplied by x1 x2 x3. How many equations do we have? Huh? So this by this equal to this by this. How many? 2, right? So each one of this, 2 here is m. So each one of this has m number of equations. Okay? Yeah.
Sorry, do you say n or
M. So this one has their m number of equations, right? M number of equations for each one. Okay. M number of equations that are here. Then in total, then how many equations do we have at here in total? How many equations? How many numbers? 0 to n minus 1. So how many did I list here? There are n numbers listed here, right? N number listed here. Each one of them has m number of equations in total. Then there are what? N times m number of equations. So there are n times m number of equations here, right? Yeah. Now, if we write this one in the matrix format, okay, if you rewrite it in the matrix format, and that's basically C at here, CG n minus 1, x of 0, okay? If you rewrite in the matrix. Okay. So now what's the size of this matrix now? C is m by n. C is m by n, G is n by n. So each one of this one here is a size what? M by n, right? Each one of them is m by n. Then in total, what's the size at here? In total, the size is what?
N by 1.
Each one is n by n. How many rows are here? So there are n number of rows, and each one has m number of rows. So altogether, yeah. Okay, it's n m by here. Okay, but what do we want? We want to see if we're able to get this x of 0. Okay, we want to able to, so objective is if we can get x of 0, okay, from this above equation. Okay, that's what we want. And what's the x of 0? X of 0 representing is an n by 1 vector, right? It's n by 1 vector here. So then here comes this dilemma here now. But this is not a square matrix, right? This is not a square matrix. This is actually way beyond a square matrix, so much larger than that, right? So you have n number of, let's say you have n number of unknowns, but this matrix here, right, is more than n by n, basically n by n here. Okay, yeah. So the question here is, if we want to get this x0 out of this matrix here, out of this equation at here, then what do we have to do? So the question here is, what do we have to do? We have to be what? We have to see if we can extract an n equations out of this one here. And not just extract n equations, we are trying to do is we're trying to extract n linearly independent equations out of this one here, so that we can solve, right? So basically it's like a ax equal to b again. You want to solve for the x, then the a has to be non-singular. A is non-singular means when you multiply a with x, or when you look at the rows or the columns a, they have to be linearly independent, right? Yeah. So the whole idea is the objective, we can get this one here. What we're looking for is, so we should extract n number of linearly independent, okay, equation out of where? Out of this guy here. Okay? So out of this star here. Because there are more than n number of equations here, right? How many rows are here? There are nm rows. There are nm rows, so there are nm number of equations. But if we can extract just n number of linearly independent equation out of this guy here, then we're good. Right? Here we're good. So that means what? That means this matrix set here has to have a rank of so this is kind of redundant matrix. So this one has to have a rank of what? N. Okay, it has to have a rank of n here. Okay, so that means the rank of this is Cg up to Cg n minus 1. Okay, this guy here should be n here. Okay, has to be n. If we can do that, then we are able to get information of x of 0 based on the y of 0. No, not y of 0, y of 0 up to y of n minus 1 here. Okay? Yeah. Now, this matrix right here, this is called observability matrix. This is observability matrix. In linear algebra, okay, when you see rank of this matrix is n, or when you see a rank of a certain matrix, so basically rank of a matrix is the same as rank of A transpose. Okay, same as A transpose. So instead of saying the rank of this one is n, we can see an alternatively, we can see rank of the transpose of this, and rank of transpose is a C transpose, and then this is a column here, right? This is a column, so column becomes a row after transpose, and this transpose here is Cg, and Cg transpose is G transpose C transpose. All right, so Cg transpose is G transpose C transpose. Right. So up to how much? Up to this G to the power of n minus 1 and C transpose. So this is what we're going to check for the observability. Okay. And this is the checking observability. Okay. Yeah. So in short, actually, in terms of controllability and observability, right, it's actually pretty straightforward. All you need to do is to check the rank of two matrices, right? For controllability, you check this matrix. For observability, and you check either this guy or this guy, right? Yeah. So how do you do that? It's actually quite easy. If when you do MATLAB, so all you need to do is you form a new matrix based on the result of C, Cg, and Cg to the power of n minus 1. You put them together, and then you check the rank of that, right? Yeah. If it's full rank, then it's observability. Okay, observable. Okay. If the rank is n, it's observable. If the rank is n over there, and it's controllable for the other one. Okay. Yeah. Any questions? Yeah. Yeah. So you can grab any matrix, then you do a check. In MATLAB, there is a command called ctrb. Okay. So when you plug in this, right now we have a GH matrix. Okay. So let's say I let it return to me of this. So MATLAB CTRB, what it does is it basically gives you the controllability matrix. Okay, so this gives you the controllability matrix H, GH, and up to Gn minus 1H, like that. Okay, yeah. So of course, if you don't want to use CTRB, you can always stack up a matrix by yourself like this. Okay, yeah. So then you can use a rank of this thing here. Okay. See what's the rank of this CO, right? Yeah. And if when you do observability, basically it's OBSV, I think. Yeah, it's OBSV here. Okay, so what do you plug in? You plug in the GC here. Okay, plug in the GC, and let's say return a certain here BOOB, doesn't matter. Okay, so then you do a rank of this. Okay, and then the results should tell you, right? If it's N, then it's observed. Otherwise, not. Okay, yeah. Okay, so that's basically observability and controllability. There is one little thing at here, okay, before we move on. Okay, yeah. Now, usually the state space equation are derived from this Z pulse trans function, right? You have the Z trans function, and we derive the state space equation. Okay, yeah. So let's see, we have h of z, okay, equal to a numerator over a denominator. Then we end up with a discrete, okay, state equation. Right? That's generally what you can do. Okay, yeah. And you can derive the different format: control canonical, canonical, or diagonal, right? Okay, or any other form. Okay, yeah. Now. And then here comes a theory, basically. Okay. Okay, here's a theorem. The theorem basically deals with the controllability and the observability in terms of this Z pulse transfer function. Okay. So what it's saying is, if the system is completely state controllable and observable, okay, if the system is completely state controllable and observable, then there is no pole zero cancellation in the pulse transfer function. So that's what this theorem says here. Okay. If the system is completely controllable, observable, then there's no pole zero cancellation in the pulse transfer function. Actually, the other way is also true. If there's no pole zero cancellation, then the system is completely state controllable and observable based on this pulse transfer function here. Right? So let me explain what this pole zero cancellation means right here. Okay, yeah. So pole zero cancellation basically is this. And let's say I have a plant. Maybe the plant is a z over z minus 0.5, who knows? Z maybe, let's say z minus 1 like this. Okay, 0 minus 0.2. Okay, let's just see. Suppose this is the plant right here, right? Yeah. And let's say this is 0.9, maybe. Let's put a 0.9 here. Okay, 0.9. So then you're designing a controller. Okay, you're designing a controller for this plant. So the plant here has a pole at where? At z equal to 0.9, right? Yeah. So when you have a pole at z equal to 0.9, which is pretty close to where? To the boundary of the unit circle. Okay? And then we were saying is the system is stable as long as the pole is within the unit circle. But when the pole is close to the unit circle or is on the unit circle, so on the unit circle means the pole has a magnitude of 1, right? So then the the stability of the system will deteriorate, right? And then it is outside, and then it's going to be unstable, right? So basically, it's close to the unit circle, and chances are you will see more oscillations, okay? Yeah. Then the control engineer probably says, okay, what we can do is let's cancel out this pole here, right? You wanted to design a controller. So here's your controller, here's your plant here. Okay, so let's design a controller such that overall the system won't have a pole at z equal to 0.9. That makes sense, right? Yeah. So he's gonna do is he's gonna cancel out this guy here. Okay, it's gonna cancel out to 0.9. So it's actually not to cancel out. You're actually gonna add something here. So you say, okay, then you say add. Really, I want to pull it where? I don't want to pull it at 0.9 now. I want to pull it at 0.5, right? So it's like this, right? Yeah. So when you do this, right, then you have this basically pull 0 cancellation. See, this is 0 cancels the pull over there. Okay. Yeah. So when you have this kind of situation, which is what we call the pull 0 cancellation, so then you may end up with, okay, so what's the transfer function for this open loop system, which is what dz, dz, h over z. So let's say you call that h over z, right? Yeah, that's right, right? That's h over z here. Okay. So if you looking at the discrete model for this h over z, okay, and then you're looking at this state controllability and the observability and the controllability, because of this pole 0 cancellation, okay, then basically the system won't be state controllable and observable here. Okay, so let me give you a simple example here and illustrate this idea. Okay. So let's suppose that I have a system with a matrix G 0, 1, 0 here, 0, 0, 1 here, -6, -1, 6, -6 here. And H is 0, 0, 1, and C is 4, 5, 1. Okay. So GHC, that's the GHC over here for the general system. Okay, the general system. Okay. Okay, so if I want to check observability, so what do? We can check. What we can do is we can check the rank. Okay, C transpose, GT transpose. Okay, and GT transpose n-1 and C transpose. So we can check this guy here. Okay, yeah. So you can use MATLAB.obs way to check this rank. Okay, check this rank. So if you check this rank, you will see that basically the rank of this one here, this is a 3 by 3. The n at here is a 3. The rank at here is actually not 3, is actually 2. Okay. Yeah. So rank is 2, basically means it's not observable, right? Basically means not observable. Okay, so in other words, system is not completely observable for this system here. Okay, for this system. Okay, so then let's take a look at basically what's the pulse transfer function of this system. What's the pulse transfer function, right? So now let's see what's the pulse transfer function of the system. Okay, if you look at the pulse trans function, so pulse trans function basically saying is we're looking for y of z over u of z, right? So y of z, you look at the this guy here, so we're looking for y of z over u of z for the pulse trans function, in this case d0. Okay. Yeah. In the previous lecture, we have derived this pulse trans function formula, right? But in this case here, you derive it slightly different. Look at lecture. I'm going to skip the step here. Okay, skip step here. So what you're going to see is actually you're going to see that the pulse trans function end up with this. Okay, you're going to put this pulse trans function at this. So if you look at this pulse trans function here, and you see this numerator has a z plus 1, and denominator has a z plus 1. So actually, really, there is a cancellation at here. There's a cancellation. All right? Yeah. So basically, because of this cancellation, and that system is not observable. So in other words, you model the system with the order n equal to 3, right? In reality, that system, because of cancellation, actually the order is not 3, is actually what? 2. Okay, that's actually 2. So mathematically, there is this so-called minimal realization. Okay, minimum realization. So you use the minimum number of state to realize the system. Okay. In MATLAB, there's a command called mean real. Okay, when you have a system set up, okay, if you apply the mean real to the system, the MATLAB does this order reduction for you. Okay, if there's no reduction for you, necessary, then it just keep it as it is. If there's one, then there is here. All right, yeah. I'll show you something maybe in the next lecture, some examples regarding this mean real things here. Okay, yeah. So sometimes when you use the numerical approach, when you use the symbolic toolbox to derive certain things in MATLAB, right? And a lot of time is you probably will notice you have some very weird results coming out because of numerical errors. And when you use this mean real to do a little minimum realization, you'll get rid of a lot of unnecessary things. Okay. Yeah. Okay. So that's basically about this controllability and observability. Okay, so you have a few exercises which are pretty simple. Okay, just check the rank of the system, right? Any question? Yes.
Did you get that PTF function or PTF?
This one here, yeah, I skipped a little bit steps here. So really, I'll show you my lecture. I don't want to write it here, so it's going to take too long to write this whole thing. I'll show you what it is. Okay. Yeah, so this is what, in detail, what I did to derive the pulse trans function. And this is your original state space model here, right? And if you take a z transform both sides, so this side here is becomes z x of z, right? And this becomes x of z. Okay? Yeah. So that basically it's what this guy here is. Okay, yeah, and then if we expand this whole thing, that's what this equation here is for. So zx1 equal to x2, zx2 equal to this, right? I expand it. All right? Yeah. So from here, there's this u of z here. So based on this one here, we can derive this relationship between x1 of z with u of z, okay, which is basically this guy here. Okay, this is this guy. And then I have this y of k equal to c of k. So basically, we have this y of z in terms of this x1, x2, x3. If you take z transform both sides, okay. But x1, x2, x3 is what's listed over here, right? What's listed here. So if you plug it here, so you get basically, okay, reduce this one just simply in terms of x1. So then you can get a ratio between x1 and y. So here's a ratio between x1 and u. Here is a ratio between y and x1. So altogether, you get y and u, the pulse trans function. So which is this, right? Yeah. Okay. So the purpose is actually just kind of to show where that zero pole cancellation come from. Okay. Yeah. Okay. Yeah. But when you derive pulse trans function, I think you should use, in general, you should use the formula we derived in the previous lecture. Remember that formula? Let me show you here. In previous lecture, when we do this discretization of this state space model, so what do we do about this pulse trans function here? There we go, right here. This guy here, right? Remember this formula here, right? So you should use this one here. Really, in general, you have a discrete state model, and in general, you should try to use this one to derive the state space model. Okay, so basically, in our case, what we have is a C. In our case, what we have is a C ZI minus G and H plus D, right? The notation wise, okay? The notation wise. Okay. Yeah. Okay. Okay. So if there's no question, now let's start on a new topic, which is the pole placement. So let's just start it, and then we'll look at the detail in the next lecture. Okay, so this is basically one of the controllers that can be very easily implemented on the experiment setup that I mentioned when you do a design project, right? Yeah. So again, let's list the information out here. This is a system. Okay, here's the system. Yeah. So for this system here, there might be an initial condition. Maybe it's not 0. Okay, maybe it's not 0. So if the initial condition is 0, then if there's no input at here, so basically the system is not moving, right? The system is not moving. But if the initial condition is not 0, okay, it's not 0, and what you really want is you want x of k to go back to 0. Okay. So the system probably not gonna go back to 0 by itself. So you probably have to put in some efforts at here so that you can bring the state, right, from the initial value back to 0, right? By applying UK. Okay, applying UK. So the question, of course, is how fast do you want it to go back to 0? Right? And if it goes too fast, if it causes an overshoot, and what will be the amount of overshoot that you desire or you don't care, right? So when you in the classic control system, when we design a classic control system, there are always a set of specifications, right? What's the rise time? What's the percentage overshoot? And what's the settling time? Remember those things, right? Yeah. So those are basically the questions is when you apply this U, how do we properly generate this U such that we can meet the specification, right? Yeah. Okay? Yeah. So this is basically an idea of a feedback control now, right? Feedback control. So if I draw this, the system here again here. So what we do is, here's a system here. So let's draw this model of the system first, right? Let's draw the system model here. So what's the model of the system now? I have an H block, I have a G block at here, I have this x of k and x of k plus 1. So the relationship between xk plus 1 and xk, basically, it's a delay, right? From here to here, it's a one-step delay. So if I have a block z to the power -1 representing the delay, and what's giving here and then out of here, basically, it's the difference is a delay at here, right? The difference is a delay. Okay. So let's say suppose this is your x of k here. Okay, this is your x of k. So then I can use this g at here to multiply with this x of k at here, right? Multiply this x of k. Okay. And what will be this plus sign here? So there's a plus. Plus what? This h by u of k. So maybe the input is u of k is over here. So the u multiplied by this h at here. Okay, multiply the h. So u multiply h, what's coming out of here? This is hu at here, right? This is hu. Okay, it's hu. And this guy plus with what? Plus with this gx of k. So this guy plus this. So there should be a junction at here. So this is a plus. Okay, so this plus this give me the so-called x of k plus 1. Can you see that, right? So when you when you basically when you build a Simulink, okay, as we're going to do a future. So how do I build a model? If I have this discrete model here already, I have the G and H matrix already now. When you build a Simulink model, this is exactly what you do. You drag a constant block here, and putting the corresponding value matrices, and you drag another block Z block here, and then do a little varying here. That's your model. Okay? Yeah. Okay. So this is your open loop, right? This is the open loop here. So basically, the U, we don't know how to generate, but it's U is control input here. But if this actually a feedback system we're designing, so what we do is, so what are we feeding back? We're basically trying to feedback is this x of k here. Okay, we're trying to feedback this. When you design a feedback system, in general, you design as a negative feedback. Okay, so what we do is there is a negative matrix k at here, and that's going to be the u at here. Okay, so this is a simple feedback system. Is that good? Yeah. So now, in this particular case, you probably wonder is, oh, that looks different because usually when you look at a classical system, what do we have? You have a reference input here, right? And then you have this feedback from the output. This is y. Then you do this, right? You do this. Yes. So in this particular case, we'll deal with that shortly. But right now, okay, right now what happens is, remember the objective, okay? The objective is we want to bring this x of k back to 0, okay, back to 0, not regulating it to a certain level. It's bring it back to 0 here, okay? So basically, you're not control this guy to 1 or to 2 or to 3. Not a reference control. It's regulated to 0. So this guy here, what we call is called regulator. Okay, it's a regulator. Right. So we're going to look at this reference control problem. Okay, yeah, but now it's just a regulator. Okay. So what's the result of regulator? It's this x of k will be 0 after certain sampling instance. Okay. So is that okay? Yeah. Okay. So if I do this, let's take a look at this. So basically, the u there becomes what? Negative k by x of k, right? The u is this. If u is this, maybe I can plug it back over here. Okay, plug it back over here. So then what do we have? We have x of k plus 1 equal gx of k minus h by u. So that's hk x of k, right? Like this. Okay. So can you tell me what will be the size of the k at here before we move on here? What will be a proper size of the k, the gain at here? We call this is a gain matrix or matrix gain.
N by 1.
Come again? Sorry, Conan?
N by 1.
N by 1? So if this is n by 1, what's the size of x here?
N by 1.
No. No. X is a n by 1, right? Can you use n by 1 times n by 1? M?
N by 1.
No, here's a single input, single output. So single input, single output, what's the u size? 1. So what should be the key at here? 1? Right? 1 by n. Okay? Yeah. So altogether, if you simplify this here, so what do they have? Hg minus hk and x of k. Okay, x of k. So with the feedback, our state space equation becomes this. Okay, is the feedback. What's the original one? The original one is this here, right? The original one is this. Now, what do we call, if I look at this, if the matrix G at here, if I calculate the eigenvalue of the matrix G, what does the eigenvalue of the system of the matrix G represent? What does the eigenvalue system of the matrix G represent? The pose. The pose of the plant. With the feedback, right? With the feedback, what is the new system matrix? It's this, right? It's this. So this guy here, it must have a different eigenvalues or different pose now. Okay? So this is basically the whole idea of pole placement. This is your new system feedback here, right? This is your new system feedback. A new system state equation. And what do we want? we want to bring this x of k back to 0. So actually, this x of k, if you do a solution here, the new x of k will basically become the based on the solution, which is what? Remember that, right? The state transition matrix. So this guy equal to this. Okay, equal to this. And this is not 0. This is not 0 here, right? But what we want is, we want this guy to go to 0. Okay, we want this to go to 0. So how do we make sure that this go to 0? Basically, we have to make sure that this matrix has to converge to 0. So if this matrix, you need this matrix to 0. Now let's consider the simple case. If this scalar case, if it's a scalar, this quantity is not a matrix, it's a scalar here, okay? It's a scalar. So what makes this guy go to 0 when k is increasing? The scalar value has to be less than, has to be what? So what makes a quantity a to the k go to 0? Or what guarantees that this guy go to 0? A equal to 0? Consider general one here. The absolute value of a has to be less than 1, right? Yeah. So then, in this particular case, this g minus hk, okay, it's a matrix, not a scalar. So the eigenvalue of this g minus hk, the real part in linear algebra, the real part of this eigenvalue here has to be less than 1. Okay, basically, the pole of this matrix needs to be within where? Within the unit circle. Okay. And the second question is, what makes this guy go to 0 faster? When the a value is close to 0, right? Yeah. So then here's the question now. If you want it to go back to 0 faster, then you have to make this eigenvalue of this matrix, right, to be closer to 0, or the origin. Okay. So how do we make that? Basically, how do we manipulate the location of the eigenvalue? Is based on what? The k at here. Okay. Apply a proper k. That make sense? Yeah. So that's the general idea of so-called pole placement. Right? So we'll look at some examples as to how do we properly design a pole placement next lecture. Okay? Yeah. Any questions? Good. Good. So we have our midterm maybe after the break, and I have some assignments here for you to pick up.